it's huge. And I remember one patient, we did a general intelligence test, and one part of the test was we have such wooden blocks, and you know, they're arranged in this way that they have different colors on top, so you are asked to lay certain patterns with these things, but always in an arrangement of 4 by 4 or something. And he was laying them not at all in this 4 by 4 thing, but was trying to then stick them up like a branch or something like that. And afterwards I said to my supervisor, so, oh, he clearly had a spatial deficit. I mean, not even recognizing that you should stay in this 4 by 4. No, that's normal. Quite a few people find these tasks quite difficult. So it's important to keep in mind that not everything which seems obvious to us is obvious to other people, and say, okay, yeah, this person has a spatial deficit or something. You usually need proper testing, clinical testing. And in the beginning, when you read a lot about these deficits, then you start seeing that everywhere, that people don't behave like that. I've heard that students studying medicine have this, quite a few of them have this period in their study time that they see all the illnesses on themselves. So is that already a rash or something when they just deal with that in the lectures? So just keep that in mind, that not everything which you would consider like not normal or weird is necessarily a clinical case. Okay, to summarize what we've heard on the dysexecutive syndrome is we have seen that one of the typical phenomena or impairments is perseveration. You can assess this using the Wisconsin card sorting test. You may have problems with distractibility, impaired inhibitory control. You may use this Stroop task. If you want to test whether there are impairments in monitoring task performance, you can use the self-order pointing task. Planning impairments can be assessed using the Tower of London task. And we have seen that utilization behavior may occur. I said it's not that common, and problems with social behavior may occur. So these are kind of the key symptoms. There is a wide variety of further things which may appear. Some of them a bit more common, some of them very rare, but some are still very attention capturing for some people. For instance, there is something, but this is often more when you have medial lesions, and again not directly related to executive control, that people won't move or act by themselves. So if you put them into a room and sit them there, they just stay there. They will not move a bit, even if they have to go to the toilet. If they are thirsty and here is a bottle of water, they wouldn't move. It's only when you then just take them and move them away, they are fully functional. To just stand up, they walk with you, they don't have any problems with that. It's just that, like we said, on the lateral surface you have a gradient, you might have that on the medial surface as well. And there is, again, very simplified distinctions that people say the lateral prefrontal cortex is usually associated with dealing with external stimuli. With the external world, there's a stimulus that responds to that. While the medial side of that is more the internal side of things. So your internal drive to move. And people may just lose that, so that they don't move on their own behalf, if you have very anterior medial lesions. Okay. Yeah, as already said, like with executive functions, the dysexecutive syndrome is hard to define in very clear-cut fashions. And the tasks which are used for the dysexecutive syndrome are basically not independent. They often overlap in the things, in the symptoms they exactly assess. So Stroop task does not only assess inhibitory control, it may also assess other aspects of reading speed and things, or this card sorting test involves inhibition, involves switching, engagement in a new task.
Is there some kind of spatial awareness needed as well?
Yeah, so it is quite a few things. So you, they have a focus on a specific particular thing, but it's not like you use one task to have exactly one component or one symptom and another task for exactly another one. It's unfortunately a bit more difficult, and because of that, it's quite hard to get a clear definition of that. Okay, again, in between, wrapping up what we heard so far, we have the theoretical concept of executive functions. What are the key functions here? We have seen the lateral prefrontal cortex is important, and now we have learned about the clinical symptoms when we have a lesion in the area. Okay, any questions so far?
Is most of the damage that relates to dissociative syndrome in the lateral prefrontal cortex?
Yes, I would say so. I mean, it's research is often a little bit limited when you work with patients, because lesions often occur randomly. They often occur systematically. For instance, because one artery supplies a specific area of the brain, and when that is blocked, then it's always that part of the brain which is then lesioned or inhibited in function or something. So it's not like just get enough participants and you will get such a nice sampling that you can disentangle each function from each other. It can be extremely difficult to do that. And to give you an idea about that, I heard this quite a few years ago. You heard of the visual system, so you heard about neglect, I guess. Yeah. So usually neglect is attributed to parietal cortex. And there was a study by Carnot. He published that, I think, in Nature in the early 2000s, who said actually it's not parietal cortex, it's a superior temporal lobe, posterior part, which is relevant for neglect. And the reason why people missed that is that the way the lesions occur is usually mainly parietal, but virtually always it also includes this posterior bit of the temporal lobe. But people just focused on the parietal lobe. And he's director of a neurological clinic, so he has access to loads of patients. And he wanted to have like a double dissociation, so patients only showing that lesion in parietal without temporal, and showing temporal without parietal. And in one of the groups he had only 4 patients, because he was not able to find more patients across a time period of a couple of years. Because some lesions are just occurring so rarely, and that makes it very hard for this type of research when you want to go into more detail. So often it's like lateral prefrontal cortex. If you are lucky, they say superior or ventral, but usually no more specific than that. Because even if you have one patient with a focal lesion, the next patient has it slightly different. So that's making it a tricky business. But it's these type of executive functions is usually lateral prefrontal cortex. Okay, so this will be the last bit we talk about today, and this is maybe a little bit going back again, a bit more detail, cognitive theories of executive functions. And again, with relation to how they may be represented, or the relation to the brain. Okay. So, when one looks at theories of executive functions, one has to deal with a couple of issues. And one is, which has been termed the homunculus problem. And that is, we talked about that executive control functions are like hierarchically higher level functions. They coordinate task processing. They are involved in, as I said, the decision that today we make potato gratin instead of spaghetti. So the question is, who is, so to say, on top of that hierarchy? Who actually decides that it will be not spaghetti but potato gratin today? So any account of these executive functions should try to deal with that. And because for a proper theory it's not sufficient to say, well, yeah, there are functions which decide what I will cook tonight, but they should offer an explanation, why did I decide for that? How do they do that? How do they come to that decision? Of course, that's an extremely difficult question to address. Another question is, and we will deal with that actually next week, whether executive functions are something unitary or whether it's subdivided. We already talked about different aspects like switching, inhibition, monitoring. Is that all done by one executive controller, or do we have multiple controllers? One for monitoring, one for planning, one for switching, and the like. And nowadays, you virtually always have to refer in some way how your theory may relate to neuroanatomy. So you have to provide some biologically ecologic validity here. Okay. The first theory I would like to present is a supervisory attention system. Did you hear from that? No? Okay. I would have thought so. It has been proposed by Norman and Shallis in 1980, basically. And this is Donald Norman. He is now an emeritus, and he is an American researcher who was at MIT most of the time. And he's very much into ergonomics, and design of machine interfaces and things like that. That was only one part of that. And this is Tim Shallis. He is now at the UCL in London, and before that he was in Cambridge, so a British researcher. And he works a lot with patients as well, does a lot of clinical studies, and I've heard that at least in earlier years recruited quite a bit at Hillingdon Hospital here as well as patients, and try to get neurological cases from here. Okay, so the model is a bit complicated, but if you have seen everything, I hope it will all fall into bits and pieces. One component is of how our actions are controlled, how we organize our behavior, is called schemas. And that's basically the lowest level, or with respect to coordination of that. And schemas are basically learned sequences of thought and action. Can start from very basic things like just grasping something, can be more complex like opening a bottle or something, and can then refer to larger things like preparing a meal also. And they specify behavior in situations like schools. If that's your situation, then do that. Follow these steps. They are hierarchically organized. So you have low level, simple actions, and very high level schemas, for instance, a schema for problem solving. There's a huge but finite quantity of schemas. So we don't have endless of them, but we have quite a lot, is the idea. And a schema is executed as soon as its activation exceeds a threshold. So how can a schema be activated? That can be either externally by perceptual stimuli, and here an example, for instance, again, is utilization behavior. You have an external stimulus, and the people not in charge of their behavior, because they can't inhibit, will just get their schema activated by that and will just do the action. Or it can be activated internally, for instance, by the output of a recently activated schema. For instance, after having finished my dinner, this may automatically activate the schema of either cleaning up the kitchen or having a coffee or something. And the idea with respect to the anatomy is that schemas are localized more posterior in the brain and not in front level. To give you some examples for illustration is, suppose you go into your kitchen and you see that there's a pile of dirty dishes. So these dirty dishes may serve as an external trigger for the schema clean dishes. This schema then itself may consist of a series of smaller or more low-level schemas, which are, for instance, first put water into the sink, add washing up liquid, wash the dishes, rinse them with clean water, and dry them with a towel. So these sub-schemas, so to say, are organized in a fixed sequence like a script by this larger or hierarchically higher schema clean dishes. And maybe that once we finish that schema, it triggers internally another schema, like put lotion to your hands after washing. Okay. So this is a graphical illustration of that, which is unfortunately not very good quality. So the idea is you have sensory information coming in, you perceive that, you analyze this sensory information, and then you have something which Norman Shell has called a trigger database, which just is, okay, this stimulus may trigger that schema. And then you have your schema which is triggered, which actually may then consist of local schemas as well. And these local schemas, and schemas generally, we should say that in a minute as well, these are these lines, they actually inhibit each other. This is called lateral inhibition. And that results in that we don't switch to closely related actions. So when, for instance, I'm washing the dishes, that I first wash them all up and then I rinse them all, and not I'm washing them up, that the schema directly rinse it, directly dry it, and is executed. Well, my plan is to first do it step by step. Okay, there are then two levels of control of how these schemas are run and selected. One level is contention scheduling, and this is a still rather basic level of control, a lower level of control. And contention scheduling is mostly used for familiar situations. So sequencing schemas for typical sequences. An example which we had before, getting ready for work in the morning. That is something where contention scheduling put the right schemas into order. Then we have this lateral inhibition, which ensures that closely related schemas are not also executed. And in addition, it ensures that we don't run several schemas at the same time. So, because it may easily be that we have so many triggers from the external outside that a couple of schemas are activated above threshold, but we can't do everything at the same time. Okay, so it's based on the same diagram, but made more complex. So we still have our sensory information coming in. We process that sensory information, and then this abstract information goes to a trigger database. And this database may trigger different schemas, which then again consist of sub-schemas, sub-actions, movements, and things like that. And contention scheduling works on that level here, that neighboring schemas may inhibit each other, for instance, and that with interest schema they may brought it to the right order for things like that. Okay, and then we have a control structure which is called SAS, Supervisory Attentional System, And this is basically the thing which is executive control, executive function. So the SAS is exerting executive control, or a description, or one way to describe executive function in organizing our behavior. So it controls the processing of schemas on a higher level. And it's able, by the SAS, or this mechanism, can override activation of schema by external triggers, or internal triggers, or by what the contention scheduling has done. So it's like a top-level control of everything. And we need control of the SAS in particular in novel situations, for instance, where there are no schemas, or when we have very complex planning and decision-making, when we have to overcome strong habitual responses, and I'm sure that's familiar to everyone, like you go on a certain route every day, and you think, oh, today I will take a different route. You are very likely to go the same route as every day. And that's because you just are in that usual matter of running your schema, and your SAS failed to guide you to the right thing. And in critical situations, which may be dangerous or very difficult, or things like that, then we place very high attention control on these activities as well. Further functions beyond those examples are that the SAS monitors the execution of schemas to intervene when something goes wrong, and that it creates new schemas. So when you move your home or something like that and live somewhere else, you need a new schema for getting to university, for instance. And the key point is now that it's assumed that the supervisory attention system is localized in lateral prefrontal areas. So we have a distinction here. Sorry, talk about in detail about that in a moment. And now we make it even more complicated. So we have again the same diagram with our schemas here, which may consist of sub-schemas, and we have two additional, they call it threads, which may influence the activation level of these schemas. And one is motivational influences, and the other one is attentional resources. And these attentional resources are basically the influences of the SAS. And it's basically this schema complex with the highest activation, which then results in action, which we follow and which we act upon. So the SAS, or suppose you have the following situation, by external triggers, this schema has the highest activation, and this only has a moderate activation. So this would be executed. However, due to some external restrictions, we may need to execute that schema. So the SAS may use its power, so to say, re-rate, and so that this can be done, this action is performed. So that's the idea in this model how the SAS works as a control and organizational structure to enable complex actions, even against our impulses and things like that. Okay, so what happens if the SAS goes wrong, if there are difficulties or something? So first, we said SAS is localized in prefrontal areas and schemas in posterior brain areas. So we have a dissociation here. And when we have a prefrontal lesion, we just lose our SAS, or the SAS is impaired and is working slower or more error-prone or something. But we do not lose the capabilities to do the basic actions. And that's exactly like Penfield described the cooking performance of his patient. Basically, she's able to cook. She can read in the cookbook, she can add ingredients, she can chop up something, she can cook something, but she doesn't in the wrong order and things like that. We organized it. So we don't lose our basic behavior. So that's what I just said. schemas are intact, but the coordination of them is impaired. So, very typical errors associated with SAS malfunction, so to say, are capture errors. That means our behavior is based on the external trigger and not our plan we had to do. In everyday life, it's the example with going the usual route to work instead taking the other route today because we had to stop at a friend's house or something like that. Another example is utilization behavior. It is just if the SAS control is missing, it's the external trigger which drives our behavior. So this model can easily explain this utilization behavior. It can explain perseveration. Because, for instance, the Wisconsin card sorting test, we are stuck to one rule. We are performing one rule. And lateral inhibition ensures in normal performance that we just don't randomly switch to other rules. And usually this is the desired behavior, that we stick with one plan and go with that rule. However, if we don't have control of or influence of the SAS, we can't change because the other rules are inhibited by lateral inhibition. So we will never get to that state that the one which is highly activated, because we are just doing that, and we still get the external triggers which drive the activation up, to reweight that and change to another rule. So this model can nicely explain this behavior as well. I'm not able to change that. Impaired planning in the Tower of London task is one problem as well. Distractibility, but without SAS, again, we have no inhibition of very strong external triggers. So in this example, reading is such an automatic response, and naming the color a word is written in is such an unusual task that having just this as an external stimulus, our normal response would be to read it and not to name the ink. So the reading schema would be much more active than the name the ink color of the word schema. And without SAS control, we just read it and are very hard in reweighting that. And you could say that the slower performance is due to this constant reweighting which has to take place before you can do the task. You have your initial response, you have to suppress it again and do the other task to perform the task. Okay, if you're interested, this can be quite nice reads. There is literature on normal human errors, so to say, of people. This is probably one of the persons having done most research on that. This is James Reason, who wrote a book on that called Human Error. But Donald Norman also had a paper on categorization of action slips. And as I said, they can be quite interesting to read because you experience a lot of these errors, mistakes from your own life. They have sometimes more extreme examples of, this is all about normal people, not brain damage or anything, of people who reported that they went upstairs in their sleeping room, in their bedroom, to get something out of the closet or something, and just undressed themselves and lay down in bed midday or something like that. So it was totally inappropriate, but it's one of these capture errors. Or you probably have this experience as well. You go to the supermarket to buy exactly one thing, let's say sugar, and you arrive home and you have 20 other things, but you don't have sugar. So these type of errors are analyzed in a scientific way, categorized, and looked into why did they arise and things like that. Often with this background of performance in work environments as well. So, but as I said, it can be sometimes quite entertaining to just read that. Okay, to summarize that model, although it's, I think, more than 25 years old or 30 years old, it's still quite popular, especially in the clinical domain, because it gives a very good account of the deficits and allows a good explanation of that, good description. Everybody knows what you're talking about when you reference that model. A problem is, from where does the SAS know which schema to activate? That's not specified. It just says, oh yeah, if you have to do that, it can reweight the activation of the schema. But why do you do that in the first place? I mean, sometimes it's evident in the Stroop task you are instructed to do so. But in everyday life, it's not always that evident. So the question is the SAS a homunculus, like a little man sitting inside our brain and telling what to do, which then itself has a brain, and we start trying to interpret how that works. Okay, any questions regarding that SAS model? Okay. So now the last one, theory for today, before we then are finished. And this is a different approach, which is somewhat related to the SAS model, but goes a step further, so to say, and therefore solves some of the problems I just mentioned. And it has been proposed by Jordan Grafman in the early 90s. And I think you can subsume that if you say the control of our actions is organized by stored memory representations. Let's just have a look what he thinks is going. So he would also say that knowledge is represented in form of schemas, like in the Norman and Challis SAS model. And however, he proposes additional units, which he calls managerial knowledge units, or abbreviated MKU. And they are kind of a special type of schema. And they're involved specifically in planning, management of knowledge, social behavior things. So they are more like the organizational thing. So not this purely behavioral thing, but more how to organize that behavior. And these knowledge units are stored in prefrontal cortex, you would say. So let's have some examples to clarify that. So these are, I would say, average level on a hierarchy MKUs, managerial knowledge units for sequential events. So this maybe is a very generic one. So it's the beginning, you have some setting, you have the beginning of the subject intention, the reaction of the subject, the goal, attempt to achieve that goal, outcome of subject, and then it ends. However, he gives some examples. For instance, eating out in a cafe. So going to cafe, arriving at the cafe, greeted by host, seated at menu received, orders food, eating, reaction to food, and payment of bill, leave cafe. It's pretty much like the schemas we have seen before. And here's another one for visiting Paris in France. Okay. They are hierarchically organized. So you have very highly specified units, which are really like, okay, exactly eating that particular type of food in that cafe. Then you have a more general one for eating out in a cafe. Then you have a more general one, eating out in general maybe. And so you go up and up, and they become less and less context dependent because they're more and more general. Until you have some very abstract